And on to chapter 8. Now, chapter 8 is the last classic neurotransmitter chapter in the textbook. And it covers two, and they are related. The opening vignette is odd. They're talking about smart pills that will enable us to generate pearls of wit, or just be smarter. Is this possible? I would say yes. We're going to have some ethical decisions to make when we can start doing that on the next page. There's more on that. I have a question, but you can't answer since I'm recording this. I have to check my microphone. Let me turn this. No, I can't do it. I just have to trust. This Marilyn Vos Savant, author of the Ask Marilyn column in the popular Sunday newspaper magazine Parade. Now, decades ago, I remember Parade as being a popular Sunday magazine. I'd like to know if you guys know about it. She's very proud of herself for being smart, and she is. And will we have pills that can do that? The term neurotropics comes up here. It's a real term. On Facebook, I find myself putting laughing icons on what I perceive to be kind of new age, mystical, flaky concepts. And I warned you about some sites that are taking some new epigenetic discoveries and turning them into kind of flaky ideas. And I saw a site using neurotropics recently. Now, neurotropics are real, but be vigilant in terms of where you get your information from. The chapter will spend the vast majority of its time on glutamate, which is a very important excitatory neurotransmitter in the central nervous system. The last maybe third, gamma aminobutyric acid, GABA, will figure prominently. It's the glutamate and GABA are the primary excitatory and inhibitory neurotransmitters in the brain. And they have an interesting relationship between each other. And I keep referring back to the yin-yang symbol, and we have it again. This ubiquitous excitatory and ubiquitous inhibitory neurotransmitters, they are remarkably related to one another, as we will see. So here's glutamate. It's the most abundant amino acid in the brain. That's pretty impressive. Glutamate and aspartate are the two principal members of a small family of excitatory amino acid neurotransmitters. They're big, and boy are they. Glutamate is the one that gets most of the press. It is very important, and it is very powerful. And as we'll see, it can literally excite neurons to death. And you take, here's the synthetic pathway. It's very simple. Glutamine, glutaminase turns it into glutamate. Zip. And it's everywhere. It's not used everywhere as a neurotransmitter, but it's everywhere. Glutamatergic neurons have greater concentration than others, although you're going to find glutamate in lots of places, which makes it a little bit challenging to study, but they've worked it out. Neurons generate glutamate from the precursor glutamine. You can make glutamate from several different reactions. That's an indication it's important because there's many ways to make it. Neurons can transform glutamate into glutamate using glutaminase, and that we've seen that in that figure already. And as the book says, it involves a fascinating metabotropic metabolic partnership between glutamatergic neurons and neighboring glial cells, especially astrocytes. I've been, saying regularly during these lectures that the glial cells, when I was you, we didn't think they were very important, and now they are getting their due, and they are very important for glutamate. And we've seen astrocytes recently. We'll see more of them in this chapter quite a bit. Now, you can anticipate what will be on the next page if you haven't read the chapter. We're going to be putting glutamate into synaptic vesicles. And it's hard to measure how much glutamate is in each vesicle. Personally, I'm not obsessed with that question. 3 distinct proteins that package glutamate, and they're mercifully named VGlut1, 2, and 3. Vesicular glutamate transporters. It complicates things that there are multiple forms, but it also means we can develop interventions that affects one form without affecting the others. Most glutamatergic neurons possess GLUT1 or 2, usually not both, and 3 is less abundant, and we'll see that it does occur and it is important, but not as popular as 1 and 2. 1 primarily in the cortex, and when you think about higher cognitive functioning, possibly schizophrenia, lots of interesting things, that should pique your interest right there. GLUT2 knockout mice, they die immediately after birth. You can't live without GLUT2. GLUT1 knockout mice do survive birth, but they don't do very well. And we'll have a figure on that in a second. And this next fact is relevant to me. GLUT3 knockouts are viable, but they're deaf. And that should tell you what GLUT3 does for a living. It's involved in glutamate in the auditory system. And before I became a pain guy, I was an auditory guy. And glutamate and GLUT3 are important in the auditory system. Not very important for this chapter, but it's an interesting fact. Co-expression is going to come up quite a bit in this chapter. Glutamate seems to exist with other classic neurotransmitters, suggesting co-expression and co-release, and this should make you think of Dale's law. And there's going to be potentially a real violation of Dale's law here. Dale just thought that neurons did the same thing at all their terminals. There may be an exception to that here. And here's the violation. The possibility exists that some neurons not only segregate their vesicle populations, but also segregate their axon terminals, so that 2 different neurotransmitters are released at separate terminals. And this is the same neuron. That Dale did not think that happened. Dopamine, glutamate co-expressing neurons of the ventral tegmental area. And how many times have we seen that so far? That may represent examples of this phenomenon. So in other words, neurons in the VTA may send projections that selectively sequester either dopamine or glutamate in terminals for release at separate parts of the brain. More often we think of these things coexisting in the same terminal. This is interesting. The cells that are believed to release dopamine alone come from varicosities that do not have classic synaptic morphology, and they release glutamate alone from their terminals. Now, when you say varicosities, we've sort of seen something like this, and I likened it to octopus arms, where the axon is going along and there are swellings or varicosities, and dopamine may be coming out of those. And often when I think about that kind of arrangement, I think about the neurotransmitter sort of watering the tissue, creating a tone for the tissue to have normal neural activity. Whereas when you have the terminals, maybe it's a little more precise, a little more dynamic with specific receptors. I sort of make that up, but it may be true. And glutamate is a co-transmitter with other classicals: dopamine, serotonin, acetylcholine, GABA, and glycine, which we really haven't talked about, but it's a little bit in this chapter. And here's new news. And when I was you, we never thought this kind of stuff. But as I said, glial cells are more important than we give them credit for. Astrocytes have come up before, and it's possible that astrocytes are releasing glutamate in very much the way a neuron would. And indicative of that, astrocyte glutamate seems to be stimulated by a rise in intracellular calcium, and neurons do that too. Some astrocytes seem to have, or not seem to, they have transporters, and electron micrographs show there's vesicles in there, and there must be transporters and storage and possibly release, or at least release within the terminal for other purposes, as we'll see in a figure in the next chapter. Sorry, the next page. Taken together, these findings indicate that gliotransmission, as it has been called, must now be taken into consideration. It's definitely possibly true. Now, after you release a neurotransmitter, you have to turn it off. And we just did nicotine onto nicotinic receptor sites, and we had acetylcholinesterase, and associated with nicotinic receptor sites on striated muscles, and it zip on and off. Glutamate, you would like to be able to turn it off fairly quickly, in part because it can kill you. So how we turn it off is interesting. We don't do it the way we do with acetylcholine, where we snap it in two. We have transporters, and we'll see a picture of those in a second. And oh, look, 5 different plasma membrane transporters. I bet they are called, and they are, EAAT1 to EAAT5. And interestingly, and vitally, and your life depends on it, astrocytes, rather than neurons, play the most important role in taking up glutamate after release. Why is this important? Because glutamate can stimulate neurons to death. Some studies have estimated that EAT2, which is associated with astrocytes, accounts for 90% of total glutamate uptake in the brain. That's big. And there's a discussion down below of unfortunate knockout mice without EAT2, spontaneous seizures, and more susceptible than normal animals to chemically induced seizures. You want the EAT2. So here's the knockout mice. I had to look like 4 times at this picture before I understood what I was looking at in terms of that mouse in C. The first 3 times I looked at it, I thought I was looking at a bat. This animal is no doubt undergoing some sort of seizure. In A, you see the blue line are the knockouts They start off pretty okay, but their weight gain drops off. And B is certainly telling. Their age. Now, on the left, you had days, now you have weeks, but you can see that their survival is diminished. And down below, you have EEG recordings using a low dose of a drug that can produce convulsions, but in normal animals at this dose, it doesn't. The normal animals, the wild type EEGs look normal, but the knockout mice are demonstrating epileptiform EEG patterns. Well, I spent many years doing epileptiform EEG research. Opiates can produce epileptiform EEG patterns. I killed many trees recording that on reams of paper coming out of an EEG machine, boxes and boxes of paper. Um, so after astrocytes have taken up glutamate by EAT1 or 2, they convert most of it by means of glutamine synthetase to glutamine. Glutamine can then be transported out of the astrocytes back to the neurons. And there's a discussion here of why not just send the glutamate back to the original cell? Well, I liken this. There were some westerns when uh, uh, you'd be transporting nitroglycerin, and nitroglycerin is a liquid and it's very sensitive to shocks, and you'd have to do all sorts of things to pack it correctly, and if you hit it the wrong way, it could blow up. And glutamate is, it doesn't blow up, but boy, is it a potent neural exciter. So the book suggests, and I can't disagree with the logic, that you take the dangerous substance, the nitroglycerin, the glutamate, and you turn it into glutamine, which doesn't do anything. It's safe. And you can transport it from cell to cell safely. And then the recipient cell can turn it back into something dangerous again because it has storage mechanisms there. There's eliminating glutamine synthetase, which is not good. There's the knockout. And there are some humans who unfortunately have this as well. The knockout mice do very badly. They die before birth. And the ones who have reduced humans, glutamine synthetase, brain deformities, the structure of the brain is different, seizures, and a short lifespan. It is not a good thing. And here comes the picture. So there's the picture of everything we've been talking about up to now. We see EAT 1, 2, and 3 in that picture. You can see V-GLUT transporting glutamate into the synaptic vesicles. You have the standard omega bodies when glutamate fuse or the vesicles fuse with the presynaptic membrane. We're not showing calcium channels, but calcium has to be involved in that. And look at the postsynaptic receptors. Graphically, they are all ion channels, and we'll be spending a lot of time talking about those. There's also a transporter over there, which is interesting. So it's not normal for a neurotransmitter to be transported into the postsynaptic cell, but here is an exception to that rule. And there's EAT1 and 2 taking it into the astrocyte disarming it into glutamine. You have the glutamine transporters out of the astrocyte into the presynaptic terminal, and around it goes. Okay. Glutamate is the workhorse neurotransmitter for fast excitatory signaling in the nervous system. The most important receptors for glutamate are ionotropic and thus fast. There are metabotropic, but most of our interest is on the ionotropic. It's everywhere. It's very important in the brain. The cerebral cortex, main neurotransmitter used by pyramidal neurons. And I've been pushing those since day 1 or day 2. So they're using glutamate. And Uh, there's lots. Look at the list of structures there. Striatum, thalamus, limbic structures, also used in parallel fibers of the cerebellar cortex, excitatory pathways in the hippocampus. You see something that involves the cerebral cortex and the hippocampus, you're dealing with probably memory and cognition and other higher cognitive functioning. Most important, synaptic plasticity. If you're learning anything in this course, you're learning it because of synaptic plasticity. If your synapses couldn't change, you couldn't change, and you couldn't learn anything. And a lot of this chapter deals with the issue of synaptic plasticity and glutamate receptors. But notice changes in the strength of, you can be involved in learning and memory, cell death. Um, in adults, you primarily don't want cell death. And as I keep saying, glutamate can excite neurons to death. And one of the best ways to get this to happen is to engage in an activity where your head is constantly hit. Try soccer. That will probably induce cell death. And we also know about football. And it's involved in neurological disorders, psychopathological disorders, including drug addiction and schizophrenia. So there's not much it doesn't do. Um, and yes, there are metabotropic receptors, but we're going to focus on ionotropic. Um, and they are the ionotropic receptors are all right. The last almost paragraph in that section. Note that glutamate receptors are also used by aspartate and possibly other excitatory amino acid transmitters that may exist. Hence, these receptors are sometimes called excitatory amino acid receptors rather than simply glutamate receptors. I don't do that. I'm not denying the truth in that statement, but I'm going to stick with glutamate. And now we're dealing with ionotropic. They are like nicotinic receptors and muscarinic receptors. Back in the acetylcholine chapter, they are defined by substances that are really powerful agonists. And you can see three in the figure on the right, and we're discussing three. AMPA receptors, uh, because AMPA is a very selective agonist. Um, the most fast excitatory responses to glutamate are stimulated by AMPA. And you can see on the right that the AMPAs are ion channels, and I see sodium, and that's fast. Second is cannate, also named by a selective agonist. It's also a sodium ion channel. Um, there's the comes from seedweed. The third is NMDA. I've done a fair amount of research with that because I'm a pain guy. And after you get injured, think about the last time you got a sunburn, you'll often sensitize to pain after that. You don't want to be touched because things that didn't hurt you before now do. NMDA receptors are probably involved in that. And I've dealt with drugs one that will be discussed later in the chapter that deal with in the NMDA receptor complex. Okay, now let's look at this figure. So AMPA and cannate, pretty much the same. And there's multiple subunits. And for these guys, there are four. And it's complicated, and it's way complicated, as we'll see on the next page. But I draw your attention to NMDA. And this figure doesn't do it justice in terms of its complexity. But it doesn't just let sodium in, it lets calcium in. And calcium, as we know, can have second messenger functions. And when you let second messenger functions loose in your postsynaptic membrane, get ready for lots of things to happen. And this process is very important for normal cell functioning and probably for learning and memory. And there's rats treated with the NBQX, sedation, reduced locomotor activity, and ataxia, uh, staggering in people, poor performance on the rotarod. You saw that in an earlier chapter. It's a rod that rotates. Protection against electrically or chemically induced seizures, which possibly can be good. And so this drug that works on AMPA receptors, possibly canate, these findings indicate that AMPA receptors are probably involved in locomotor activity, coordination, and brain excitation or excitability. Oh my goodness, look at that puppy. There's your NMDA receptor. I'll just let you look at this for a second to glory in its complexity. You have multiple sites for glutamate to dock, but you also have co-agonists, that's discussed in the right column. You have glycine and D-serine docking sites. So I know I will oversimplify and often say, glutamate receptor sites or NMDA receptor sites, but really it's a receptor complex. There are 4 transmembrane proteins there. They each have different characteristics. They can bind glutamate, and I'll simplify by just saying glycine. And if you don't have those sites occupied, this thing isn't going anywhere. But look down the throat of that ion channel. You have magnesium down there. Now, some of the flaky sites that I laugh at on Facebook, they will push magnesium, and magnesium, oh, you need it. You definitely need it. But some of the flaky sites overemphasize magnesium supplements, but you need it. But look what it does. It sits in the ion channel that the NMDA receptor has carefully crafted, and it's stuck there. And as long as it's stuck there, those beautiful little blue and white balls can't go through the channel. No matter how much glutamate and glycine / D-serine you release onto this receptor complex, you can flood it. And as long as that magnesium is sitting there, nothing is going through that channel. This is a weird receptor complex. It is ligand sensitive, glutamate and glycine, and of course NMDA, but it's also voltage dependent. The cell membrane sits at the resting potential often, and it's charged at, let's say minus 70. And at minus 70, that magnesium is going nowhere. But as the cell becomes slightly depolarized, and we'll see that's another receptor doing that, because it can't be this receptor, because this receptor can't let ions through because it's clogged with magnesium. But as this cell membrane becomes less negative, slightly depolarizing, this receptor complex notices, voltage dependent, it flexes, and it causes the magnesium to undock. And the magnesium can then float up out of that channel, and then the channel is available for sodium and calcium to flood through, but not, of course, if PCP is there. PCP is a recreational drug. It's not part of the normal nervous system, but it docks down there. And if magnesium can block that channel, PCP can too. It's important to the channel, but it's not important to the normal functioning. So on the right there's a discussion of co-agonists, not receptor agonists, because there are different points on the receptor complex. And there's a discussion of voltages and depolarized. Depolarized is such a strong word. I prefer hypo, like hypothermic, means you're a little colder than normal. it doesn't mean you have no temperature. Depolarized really means you have no polarization, but that's the way we use the term. Um, it's gentle depolarization can cause that voltage dependent NMDA receptor to kick loose the magnesium and open the channel. Um, oh, right. So who's doing this? Where's the excitation coming from? In this chapter, we will emphasize AMPA receptors, not so much CAN8. We're going to focus on AMPA. But remember, up to this point, we were very happy with acetylcholine landing on, say, a nicotinic receptor and causing sodium channels to open and sodium to enter the cell, and positive ions entering a negatively charged membrane will make it more positive, and it can hypopolarize it, possibly to the point where the voltage dependent sodium channels fire and you get an action potential. So it's complicated, but it's important. NMDA receptor is a biological coincidence detector. Isn't that a coincidence? Two things occurring together in time. I used to do a lot of computer programming and a lot of logic wiring using real wires. And we had these things that I would wire up that were called AND gates. And you would put wires into the AND gate, and you could putting one would be ridiculous because you can't have an AND with one, but you can put in 2 or 3 or 4. And the circuit notices how many wires there are. And that circuit will not fire unless all of those wires are active. And let's keep it simple, just 2. So in an AND gate, you have to have this and that for something to happen. That's a coincidence detector. And the text is putting a lot of emphasis on that, and with good reason. And we're going to be talking about Pavlov, and not too much, but just a touch of learning theory shortly. Just revel in that. Be amazed that you live in a world where researchers can study ion channels and receptor complexes and understand them to that level. That is amazing. Just be in awe. Just be impressed. The simpler images tell the story quite as well. MK801. It is a non-competitor antagonist. It works on the receptor complex. It does not work on the receptor complex at the glutamate receptor. It works on the NMDA receptor complex. This is what I used on my beloved snails. I was doing such good things with the incredible edible snail. If you've ever eaten snails in a restaurant, they were my snails. And after injury, humans and snails sensitized to additional stimulation. And I discovered that if you gave the snails MK801 after the injury, you could block one form of sensitization, but not another. And I found if you gave another drug, I could block that one, but not the first one. I had a beautiful story. And then because of 9/11 and Homeland Security taking over regulation of agriculture, an inspector came into my lab and decided I had too many doors and I could not be trusted with having snails in there because eco-terrorists could break in and take them and release them into the ecosystem of Pennsylvania. And I kept saying, these snails can't survive winter. They cannot burrow. They cannot protect themselves. As long as there are winters, these snails will never live here. It made no difference. They took them and I had to stop my research. And here's a discussion of both PCP and ketamine. Now, I don't hear anyone talking about PCP for therapeutic purposes, but ketamine is being discussed now. They mess you up. They can be taken recreationally. Interesting. Memantine can help people with Alzheimer's. So yin and yang sounds like yin and yang to me. Uh, and they seem to share the same or similar docking location on the NMDA receptor. Uh, you may be following the news on antidepressants, and the FDA just approved a ketamine based treatment for depression that can work remarkably quickly. I have high hopes. It's not magical, doesn't work on everybody, but it's definitely progress. Then we have the metabotropic, which we're not going to spend much time on. But look at that, man. 8 different metabotropic receptors types. And they're numbered 1 through 8. And there are different types and they do different things. And you see down here the group 3 are autoreceptors. And autoreceptors, if you're an agonist for an autoreceptor, you're basically telling the cell, hey, you're releasing enough of this stuff, there's no reason to do more. So if you do an agonist for that one, you are suppressing glutamatergic receptors. Okay, so we're going to move off that topic pretty quickly. They're important for motor activity, cognition, mood, and pain perception, right? There were some new pain inhibitory systems that may be involved in this, but I've sort of moved out of the pain area, so I'm not following that. And then there's Fragile X rears its head, and Box 8.1 is pages of information on Fragile X. This is a bad one. It really leaves the person cognitively impaired. And this is an ode to animal research fairly quickly being used to help people. Spoiler alert, it didn't help very much. But translational medicine came up earlier. The NIH has a bench to bedside system that, quote, research teams seek to translate basic scientific findings into therapeutic interventions for patients and to increase understanding of important disease processes. NIH 2017. So, yeah, it's important. It's good. I hope it works. We know it causes Fragile X. Mutations of the FMR1 gene. And I forget what there's anything in this section I wanted to point out. Mental retardation. It structurally changes neurons. We can see these things. And in this box, I vote out of sequence. The book mentions LTD, long-term depression. Now, without reading the rest of the chapter, you're going to see long-term depression, and you're probably going to think about clinical depression, which this is not. This is a change in neural excitability. It's related to membrane potentials and hyper and hypopolarization. And it's very related to long-term potentiation, which is down the bottom, which may be very important for memory formation. So don't get too distracted by that. But FMRP may be very important for long-term depression. The field is obsessed with LTP, but LTD must exist for a reason. It must be important. Again, the yin and yang of neuroscience. It's important. So now we're talking about metabotropic receptors and hoping we can help people with Fragile X. And when they did this in animal models, it seemed to work very nicely. You could even see structural changes in neurons. And then they tried to do the most scientifically rigorous thing you can do with the drug, double-blind, placebo-controlled clinical trials. Neither the person getting the drug nor the person administering the drug knows what the drug is. And everybody thinks they're getting the same stuff. They could be told they may be getting nothing, but at least they're all told the same thing. And they did it. On the next page, you'll see that they ran the trials, I think, for 12 weeks. It didn't do much. And they canceled the program. The drug companies are corporations. They're not humans. They're made to make money. And the drug trial failed. And the money-making organism that is the corporation pulled the plug. And hopefully someone will follow up on this. And there's more. There's a discussion about why it may not have worked, and 12 weeks may not have been long enough. And then there's mGlu-R theory of Fragile X. It's a very good and rigorous discussion. And there's the normal, there's the Fragile X, there's the corrected as we would like to correct it, but that trial tragically did not work, and the corporation decided to go do something else to make money. I just want to make sure I'm done. So I deflected into the clinical applications before dealing with the text up above. And this is the majority theme in this chapter. AMPA and NMDA receptors play a key role in learning and memory. Yes, they are both glutamate receptors. They are usually found together, and they interact in interesting ways. Cognitive enhancement by AMPA receptor. So chapter 7, nicotine. So there we did muscarinic and nicotinic to enhance cognition. Ampakines, trying to modulate AMPA receptors to enhance the effects of glutamate without directly affecting the receptor. Remember, I talked to you about antidepressants and the reuptake inhibitors. They affect your own neurotransmitter. We don't flood the postsynaptic receptor site with drugs. We modulate the turning off of the neurotransmitter so that when your neurotransmitter, your own neurotransmitter is released when you want to release it, it's more impactful. And that theme comes up here too. These compounds positively modulate AMPA receptor activity. That is, they enhance the action of glutamate, but they don't directly affect the receptor. I love that. And now we have to skip through the Fragile X. And this is almost real life. The monkeys often get to choose when they do this game, and they have a computer monitor and they have a joystick, and they have to move the cursor with the joystick into a circle. And the monkey is saying, "Okay, computer, I'm ready. Test me, man." And then the stimulus comes up, and the image is presented, and then the screen goes blank. And the monkey says, "Dang." And the blank screen is there for 1 to 30 seconds. Now, we've done research in mice and presumably monkeys, and we know that this delayed matching to sample, it relies on different kinds of neural processing than just see a star, respond to a star. It requires some neurophysiological magic to retain that memory in that blank. And then it comes back and you pick the star. And IV injection, at the bottom of that box, IV injection produced dose-dependent improvement of overall performance. And there's the figure with CX717, which means it still uh, doesn't have a name for commercial purposes. But that's pretty impressive. I'm happy. That's cognitive enhancement. Um, this is interesting. Among other changes, aging rats show shortening of the dendritic branches, of pyramidal neurons. I've heard of them in the hippocampal CA1 area. Now, in this chapter, we're going to be saying much more of the hippocampus, and you'll see CA1 in a graphic representation, and you'll see the pyramidal cells. So the dendrites get shorter, and middle-aged rats. Rats, they're not great long-term pets. They only go about 2 years, and they're 10 months old, so they're middle-aged. And they gave them CX 929 for 3 months, and then they sacrificed them and looked at the pyramidal neurons, and they looked like the pyramidal neurons of younger mice. And figure 8.8, which I think is on the next page, we'll get to look at that. And it also, they had longer dendrites and they had more spine density. And I'm obsessed with spines. Spines can change in seconds. And sadly, we do it in humans and it's inconclusive. Okay, NMDA receptors, learning and memory. And remember, NMDA receptors are related to MK801. And these are the ones I was studying with sensitization to pain. And that's a form of memory. You remember your injury. It's well established, decades of research, that release of glutamate from an axon nerve terminal coupled with strong activation of NMDA receptors in the postsynaptic cell can lead to strengthening of that synapse. And that's LTP. And unfortunately, it's being introduced after the box, where it was stuck in there too. And LTD, we're not going to talk about here virtually at all. And that would be the flip side of this. And there's the coincidence detector, and I would prefer to call it an AND detector because the NMDA receptor requires both ligand activation, and there are two, and I'll stop saying them, I'll just say glutamate, but we know it's more complicated than that. And also a hypopolarization of the postsynaptic membrane. And okay, so these are the rats from that research on the other page. Now, personally, I like my apical dendrites going up to the top of the page, but in this figure, this is the apical dendrite. It bothers me, but what the heck. And you can see that the animals that are getting the MAAK, they have dendritic lengths that are just like the young folk, longer than the mature middle-aged rats, 10-month-old rats, who have shorter dendrites. Now, on the right are very high resolution images of dendrites, and I think that's an apical dendrite. Yes, apical dendrite. And on the left, you have the mature middle-aged animals, and on the right, you have the animals who've been treated with the drug. Now, just look at it for a while. It takes a while before you see it. There are dendrites on both, but you can see, I believe, that the ends of the dendrites on the treated animals are more robust. And they also suggest that there are more in them. So that's a good sign. And now we get into Pavlovian classical conditioning, and they mentioned Bell's and meat powder, and Pavlov won the Nobel Prize, but he did not win it for this research. He ran it for other research. He won it for other research. Um, and now we're going to be talking about coincidence detectors or AND gates and NMDA receptors. We're getting to that. So now we're getting to mechanisms of LTP. It's hard to believe it's been 40 years. Seems like yesterday. And at first, some people didn't believe this, in part because, see these words down below, tetanus and tetanic stimulation. That's very aggressive stimulation. You put an electrode in there and you really pound on the axons, creating virtually maximal production of active potentials. That's not the way the nervous system normally works. The nervous system does not like to be driven to the point of basically fatigue. And that's what led some people to believe that it was true, but it was only true for this weird situation. I don't think we worry about that very much anymore. And so this research, thousands, as it says up on the top, powerful impact on neuroscience. It has given rise to thousands of experiments. It's big, and it's complex, and we'll see. The text, I think, simplifies it nicely. Here's a graphic of classical conditioning. The pale pink is weak, and the dark purple is strong. And there's in neuroscience, they often talk about, in terms of learning, a Hebbian synapse, and Hebb proposed that neurons that fire together wire together, that they actually physically change their terminals to strengthen synapses and sometimes grow them together. This is similar to that. So you have NMDA receptors, and there's the weak stimulus hitting that one cell with an NMDA receptor, but it's associated with a stronger stimulus, and the nervous system eventually learns that the strong is predictive, is related to, or that the weak is predictive of the strong. It's something you should be paying attention to. Bell-mead powder, Bell-mead powder, Bell-mead powder, and finally, the CS no longer has a pale pink connection. It has a dark purple because of LTP, potentially. And now we're getting into the hippocampus. And this is a good picture. If you look at the hippocampus here, the pale blue, it should remind you in shape of, I believe, the number one consumed fruit in the United States, if not the world. And it should also remind you a bit of Sesame Street. The forebrain is brought to you by the letter C, or backward C's. And the fruit is the banana. The forebrain, even in rats, is growing more than simpler vertebrates. And in us, it's even more pronounced. And you have a skull, and the brain is stuck inside the skull. And this long structure is trying to grow, but it can't grow because there's a skull up there. So it bends over, and it forms a C shape. So you sacrifice your animal, you quickly take out the hippocampus, which is very easy to do, and then you slice it. That's a cross section, and you slice it and you put it on a nylon mesh in a beautiful warmed bath with oxygenated artificial cerebrospinal fluid, and it has nutrients, and it's warm, and it has oxygen, and that tissue slice can live in there for hours. And fortunately for us, the cells are oriented basically two-dimensionally once you slice it out. It's not a ball. It's horizontal. And oh, look, pyramidal cells. I've heard of them. And they have apical dendrites that go up from the top of the pyramid. And granule cells, we've heard of those too. They hold hands. Let me draw your attention to some points here. Here you have the perforant path from the entorhinal cortex, which I don't think we've mentioned, and I'm not sure we'll mention again. But these axons are forming what's called the perforant path. Now, see this line here that goes under the green plus? That line means there's brain on the left of it and there's brain on the right of it, but that line is a crack. That's not the brain. That's separated. Those axons should have taken the long road around South America or Africa to get here. They should have stayed in the nervous system. But they decided, the heck with that. The target is right over here. We're going to jump across this little crack. We're going to perforate the dentate gyrus, and we're going to go directly to the granule cells. Nicely named. Well done. And the granule cells have axons that go to the apical dendrites of pyramidal cells in CA3, and then the pyramidal cells of CA3 send their axons to the apical cells of the pyramidal cells of CA1, and this is what is discussed a lot in this section in terms of LTP. It's a beautiful system. Beautiful system. This is an important point up here. Early LTP, not excitatory LTP, but early LTP is an induction phrase, and an expression phase. So what causes those? Well, we can study those. And we know that the induction requires NMDA receptors. How do we know? Because we can stimulate the heck out of these fibers, but we can give receptor agonists for NMDA receptors, and you do not get LTP. But if you let LTP develop without the antagonist on board, and then go to test it later and give the antagonist during the testing, it still works beautifully. So the NMDA receptors are needed to produce the LTP, but not to express it. We'll see pictures regarding that in a second. Okay, so these are simplified. I have trouble with these because in all my other books, NMDA receptors are on the left and AMPA receptors are on the right, but it's not functionally significant. Notice that the NMDA receptor has a little magnesium ion in its gut, and there's your presynaptic terminal releasing glutamate, which of course can affect both of them. And the AMPA receptor can allow sodium in, which is going to reduce the polarization of that cell membrane. With the magnesium in there, the NMDA receptor isn't going to do anything. But as the cell depolarizes, we get to what happens after the tetanic stimulus. You're releasing glutamate, a lot of it. And the AMPA is doing what the AMPA does, but now look at the NMDA receptor. What's missing? What's missing is the magnesium, because the postsynaptic membrane has become less negative. It has slightly depolarized. The conformation of the voltage and ligand-dependent NMDA receptor changes. The magnesium floats away. And now when glutamate hits it, oh boy, here comes sodium and calcium. And LTP happens. And we'll get into more details on that in a second. And on the right, you're looking at the EPSP size before tetanus and after tetanus. And there you go. There's LTP. All right, good. We're getting there. Um, receptor trafficking. Now, this is the magic of how LTP lasts. Where do receptors come from? Well, they're synthesized. They're synthesized in the cell, and they have to be transported to the cell membrane and inserted in the cell membrane. And don't forget the that video I had you watch with and without the dialogue. Well, second messengers can do a lot of things. And there's the calcium calmodulin kinase 2 and other protein kinases affecting what looks like a vesicle. And what's on the vesicle? Ooh, extra AMPA receptors. And that second messenger effect causes those AMPA receptors to be moved to the cell membrane and inserted in the cell membrane. And suddenly they pop out of the other side of the cell membrane. And that postsynaptic cell now has more AMPA receptors. And what do AMPA receptors do for a living? They let sodium in. So the next time you get a burst of a neurotransmitter out of that presynaptic terminal, it's going to hit more receptors, and it's going to have a bigger effect, and you're going to have LTP. There's also discussion, by the way, of some LTP being caused by changes in the presynaptic terminal, possibly because of gaseous neurotransmitters being released, which from the postsynaptic membrane and blowing over here and causing changes that causes more glutamate release. Don't forget that some of these, think of Viagra, can go out here and affect blood vessels and increase blood circulation. So that's pretty impressive. More than 50 years ago, two researchers published a report showing MSG could destroy the retina. Don't take this message home and think that eating MSG is going to destroy your brain. It's common in some foods, and in normal doses with a normal blood-brain barrier, you are A-OK. It can't get in and it can't do anything. But long ago, I was interested in the arcuate nucleus, and there's a picture of it there. It's part of the hypothalamus, and it's just above the pituitary stalk, and it's very important for a family of opioids. And pinky rats, baby rats, they're born before their nervous system is fully formed up. And the blood-brain barrier in the arcuate is not well established. And if you inject them with MSG, you get this. On the left, there's a normal arcuate nucleus, and all those purple guys are thickly, organized cells. And on the right, that's an MSG treated animal. Some of these cells contain opioids that go to other parts of the brain, which is why we were doing it. Just thought I'd share. But again, do not fear MSG for this purpose. But now let me tell you another horror story that may make you fear MSG. I have a colleague, and the colleague says that if he eats any MSG, he gets a little weird, and he doesn't like it. So he obsessively monitors whether there's MSG in what he eats. I would bet the rent that he has a weak blood-brain barrier somewhere. And if we could get him in a PET scanner or an fMRI scanner, probably the latter because it's not radioactive, and we gave him MSG, of course, we would do it blind. I bet part of his brain would light up, but I don't work at that kind of school. We don't have one of those. So there's a picture about the receptors docking. There's MK801 again, and I miss my snails. Necrosis is the kind of cell death you get when you overstimulate cells with acetylcholine. Go play soccer or football or box. But cell death isn't always bad. We have programmed cell death during uh, development of the nervous system. And this toxic cell death is necrosis, necrotic tissue, rotting tissue. Apoptosis is the planned kind. And if you love neuroanatomy, and I do, you can look in there and you can see which is which. Apoptosis is good for you. It's made to be that way, not necrotic effects. Muscles, domoic acid. Mussels are filter feeders, and some things that float in the ocean produce a neurotoxin. And mussels are happily filter feed that and concentrate it. And 87, Prince Edward Island, on our side of the continent, they had contaminated shellfish, mussels, and they had a lot of symptoms, and some died. 3 died. This acid seems to have a particular affinity for the hippocampus, and it seems to affect it differently in males and females. I used to be very obsessed with this. I still fear mussels. Canada started testing for this before we did. We were still getting people sick down here from this, and we weren't testing, but now we do test. But a husband and wife team each had the same number of mussels for dinner, and they went to bed and they woke up, and the woman was fine, and the guy lost short-term memory for the rest of his life. Fortunately, he taught basic physics for a living, and they would just wind him up and send him into class, and he could still apparently do basic physics lectures. But he had to write notes to himself about where his car was and stuff. You don't want this to happen. But I do like mussels, and they may be a very ethical way of producing protein. The Birds, Alfred Hitchcock. This is another story with neurotoxins. And I have a picture up here somewhere. Arcuate. Here we go. So this is an old movie. You probably haven't seen it. The special effects are marginal. But it's pretty scary, as Alfred Hitchcock tended to be. And it's spun out of home. There's the source of many of my childhood nightmares, rotary phones. There was a real story where seagulls just started flying into buildings and windows and people, and it was from toxins from the sea, sort of related to the mussel story. And Hitchcock took that and turned it into a pretty disturbing movie. Okay, now strokes. So there's your stroke, but it disrupts the blood-brain barrier. Why do we have the blood-brain barrier? Blood, unfiltered, kills neurons. You want it in your blood vessels. You do not want it running through the brain. So you get this area around the destruction, which they refer to as the penumbra. I have that up here too. I'm used to running into that term in relation to eclipses. So here's a lunar eclipse where the moon is going to go through the shadow of the Earth, but where the shadow is absolutely dark, that's the umbra. That would be where the lesion was in the other example, in a sense. But around it, there's reduced light. You can definitely see darkening, but it's not absolutely dark. That's the penumbra. And there you go. You learn some astronomy and some neuroanatomy. I used to put holes in rats' heads with electrolytic lesions, electricity, and that disrupts the blood-brain barrier. And we would sometimes check to see if the barrier had fixed itself. If you inject an animal with blue dye, an intact blood-brain barrier won't let the dye into the brain. The brain will be just as if the dye was not there. But oh my, if you have just put a lesion in the brain and put a little hole in the blood-brain barrier here, in rats, the entire half of the brain may get dye in it, which means that blood is going to be messing with neurons and making them dysfunctional in a very large area. It takes a couple of weeks for this usually to firm back up. And that's why you can have quick recovery from some effects of strokes. But other effects, which are caused by this focal destruction, are going to definitely take longer to recover. Amyotrophic lateral sclerosis. This is a bad one. I know several people who've had this. Lou Gehrig's disease. Geez, I hope we can fix this. I hope we can fix this. I keep seeing new discoveries on it, but I'm my best friend in one of my best friends' mother died of it. It's not a good way to go. Now, because we are done with glutamate and we're about to do GABA, I'm going to stop here intentionally, in part to check my mic because I had trouble with my mic earlier.